Hello everyone, thank you so much for tuning in this morning. My name is Emmanuel Cook and I'm a third-year master's student at Dalhousie University studying with David Barkley, and today I'm going to be presenting my work using a real-time observatory to link ambient noise measurements to seasonal patterns of ice in the Northwest Passage. I'm going to turn off my camera because I am not sure where to look, but I will turn it back on for the question period. So the Arctic Ocean is the northernmost body of water in the world and features constant ice cover, which causes unique underwater propagation conditions and new sources of noise underwater. So the ice acts as the ice causes temperature and salinity profiles that create this shallow water propagation channel, and noise that travels in this channel will interact with the ice, and the ice will add new sources. So here's a look at the observatory that I'm working with. It's located in the western part of the Lancaster Sound in our Canadian archipelago. It's called the Barrow Strait Real-Time Observatory, which I might sometimes refer to as BSRTO, which is not that much shorter, but anyways. And it consists of a network of underwater moorings that communicate using acoustic modems. So these underwater moorings will communicate all their data to an underwater data hub, which is connected to a shore station via an 8-kilometer cable, and then all the data is transmitted to a server at BIO using satellite. So there's a lot of sensors at this observatory, but I specifically have been working with the hydrophone and the upward-looking sonar. So the hydrophone is on the hub mooring, 159 meters below the surface of the water, and will record for 1 minute every 2 hours, and then output a 1-minute spectrogram of the sound pressure levels. The upward-looking sonar will measure an ice draft every 3 seconds, and then will output a 2-hour ice draft distribution and send that via satellite in real time. So starting off with the ice draft measurements, here we have plots of the ice draft distribution sent in real time from 2018 to 2020, starting in September of 2018, and we start to see here how the ice conditions change over the year. So we have open water in September and October, with some larger ice flows flowing over the sensor. Then when we hit the end of January, the mean draft will increase. We hit shore fast ice, and then it'll increase over the winter. There will be increased roughness patterns until we hit the melt period at the end of June. Then it's very quick melt period, and we're back to open water by mid-July. And this is very similar from year to year, but as we see, the difference between the winter season of 2019 and 2020 is that we have a shorter period of shore fast ice in 2020 because of the later onset of this type of ice, and then that means there's not a lot of time for it to become thicker, and it melts very quickly at the end of June, leading to an earlier open water season. Now let's take a look of what this all means, or what this all looks like from a different perspective. So this is a satellite image of the area in April 2020, and we start to see the land here with these topographic features. There's shore fast ice, so ice connected to the land. This is this white featureless zone. We have open water, which is this darker area, and then we have large ice flows coming through, which are these white spots in the open water. And we can start to see the different mechanisms that could come up here. So breaking off of ice blocks would create noise. The collisions of these ice flows would create noise. Cracking in this ice sheet is another source of noise, or wind blowing over the ice sheet and making the small specks of snow and ice travel across this ice sheet would make noise. So now let's see how the seasonality of the ice affects noise levels. So what we have here is power spectral density on the y-axis over the calendar year. And we have data in different colors from different years, but in green we also have historical data collected by Hutt in 2012. And on the top we have a descriptive characterization of the seasonal ice conditions. So we have shore fast ice, ice breakup, open water, and freeze up. And these are noise levels, monthly noise level distributions between 10 and 1,000 hertz. And the lines are the 90th and 10th percentile of that distribution. So what we're starting to see here is, in general, we have our lowest levels during the winter shore fast ice season. We have our highest levels during open water. And then we have our levels increasing with the ice breakup or ice melt periods. So the 2020 data in purple increases to its max level sooner than the 2019 data in blue. And that's because, as we've seen earlier, the ice melt period ends much sooner and is much quicker in 2020. So the levels reach their maximum earlier. And then what we see during freeze up is highly variable levels. So this is a period where you don't have as much shipping and you have the accumulation of large ice floes. So that leads to periods of very loud moments, or it leads to very loud periods, and then times of also very quiet when you have low winds and not as much human activity. All right, so now that we know how the ambient noise levels are changing with season, let's see how that change varies with frequency. So here we're showing mean noise levels distributions per frequency divided in color by the seasonality of the ice. And what we're showing is the 10th percentile of those distributions and the 90th percentile. So at lower frequencies, regardless of the seasonality of the ice, the distributions are not changing. So you have high variability, but it's not changing because of the seasonality of the ice. Now at higher frequencies, we start to see a change. So as you go higher in frequency, your levels become a minimum during you have your minimum levels during shore fast ice and your maximum levels during open water. Another thing you see during shore fast ice is this thinning of the distribution, so less variability in those levels. Another way we looked at the data is using an autocorrelation plot of the 1-minute spectrograms, where we're taking monthly time series of ambient noise levels at about 1500 hertz, and we're comparing it to itself. And if it's very similar to itself, it will be in red as a high correlation, and if it's a low correlation, then it will be in blue. And what we start to see is these periods of open water have high correlation for very long lags, suggesting that the source is affecting the levels during these times very slowly in time as well. So that could be wind wave interactions or constant shipping. During breakup and freeze up, we see the correlation strength drop off very quickly. And that's because when there's more ice cover, we start to have more transient sources. So ice cracking, ice ridging wouldn't necessarily correlate very well over longer lags. Another interesting feature of this plot is this periodicity during freeze-up, where correlation strength increases over a 24 and 48-hour period. And this is because of how the flows and the tides interact to make noises. So What we're seeing here is a periodicity that is due to the tides forcing collisions between ice flows or increasing stress in the onset of shore-fast ice, which would increase cracking events. So this is all nice, but what do the sound levels, or what does the noise actually sound like underwater? So we get our data in real time, but on a yearly-ish basis, the sensors are recovered and the observatory goes through some maintenance. So in 2019, we were able to get the saved wave files from the sensor. Okay, here I'm going to really briefly go over some examples of what we're hearing. So at the observatory, so these are spectrograms with frequency on the y-axis and time on the x-axis. In the first recording, we're going to hear ring seals, a little bit of ice noise overlap with mooring noise. In the second recording, we have walrus knocks. And in the third recording, we have a loud day with a lot of ice noise. So that was a really quick tour of what we hear underwater. So what I shared today is just a background understanding of what the ambient noise levels are in at BSRTO, and how those levels change with the seasonality of the ice. So the next step will be to get solid correlations between the forcing mechanisms, so wind, tides, and ice, and how those relate to ambient noise, and then model them, model the ambient noise levels for each ice season. So thank you very much. I'm ready to take questions.